In episode 81, titled Cross-Validation, K-Fold Logic and Common Misinterpretations, we focus on one of the most practical habits you can build when you have limited data and you still need an honest estimate of how well a model will generalize. A recurring mistake in applied data work is treating a single train and validation split as if it is a definitive verdict, when in reality it is just one roll of the dice. Cross-validation gives you a disciplined way to reduce the influence of that luck without pretending uncertainty has disappeared. It is not magic, and it is not a way to make weak models look strong, but it is a reliable way to keep your evaluation from being held hostage by a single arbitrary split. If you internalize what cross-validation is truly estimating, you will also spot the most common misinterpretations quickly and avoid conclusions that fail under scrutiny. Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. At its core, K-fold cross-validation is a structured rotation of what counts as training data and what counts as validation data, repeated multiple times so you can observe performance across several different slices of the same dataset. You start by dividing the available labeled data into K roughly equal parts called folds, where K is a chosen positive integer that controls how many rotations you will perform. In the first rotation, you train the model on K-1 folds and validate on the remaining fold. Then you repeat that process until each fold has served as the validation fold exactly once. This rotation matters because it ensures every observation participates in validation exactly one time and in training K-1 times, which is a fair use of scarce data. The final output is not a single score from a single split, but a set of K-scores that collectively describe how the model behaves across different partitions. The reason we average across folds is not because averaging is fashionable, but because it dampens the influence of an unusually easy or unusually hard split. Any one split can accidentally concentrate tricky cases in the validation set, or, just as easily, leave them mostly in training, and those accidents can swing your score in either direction. When you compute performance for each fold and then take the mean, you are approximating what you would expect from a typical split rather than betting on one particular partition. This is especially valuable when data sets are small, noisy, or heterogeneous, because those are exactly the conditions where a single validation set can mislead you. The averaging step reduces the temptation to overinterpret a number that is really an artifact of sampling, and it nudges you toward evaluating the model's expected behavior rather than a best-case snapshot. However, the average is only meaningful when the folds are built in a way that respects the structure of the problem, and class imbalance is one of the first structures you should think about. When your labels are uneven, random splitting can create folds where the minority class is scarce or even absent, which breaks the usefulness of many metrics and creates unstable training dynamics. Stratified folds address this by preserving the class proportions in each fold as closely as possible, so each rotation has a validation slice that resembles the overall label distribution. That is not about making the evaluation look better, but about making it comparable across folds and representative of the real-world mix you care about. If you ever see cross-validation results that swing wildly on an imbalanced problem, one of the first questions to ask is whether the folds were stratified appropriately. Even with well-formed folds, cross-validation can be invalidated by leakage, and leakage often sneaks in through preprocessing. The safe mental model is that anything learned from data, including scaling parameters, imputation values, feature selection thresholds, and encoding mappings, must be learned only from the training portion of each fold. If you fit pre-processing steps once on the full dataset and then cross-validate a model on the transformed data, you have allowed information from the validation folds to influence the training process indirectly. That influence can be subtle, but it inflates performance estimates because the validation data has already shaped the feature space the model is using. The correct pattern is to treat each fold like a miniature end-to-end pipeline, where pre-processing is fit on the training folds and then applied to the held-out fold, repeated independently for each rotation. When you understand leakage as a broken boundary, the rule becomes intuitive. The validation fold must remain unseen in any form that involves learning from it. Time series data adds an additional boundary that random k-fold splitting violates because the order of time is itself information. If you randomly shuffle a time-indexed dataset and then split into folds, you risk training on future observations and validating on past observations, which is backwards for any scenario where you want to predict what happens next. That error often produces impressively high scores that evaporate the moment you deploy because you inadvertently gave the model access to future patterns through the training folds. Time-aware validation keeps the arrow of time intact, typically by training on earlier periods and validating on later periods, so the evaluation reflects a realistic forecasting or detection setting. The key idea is not the exact method name, but the constraint. The validation data must represent the future relative to training, not a random mixture of past and future. If you remember that, you will avoid one of the most damaging misinterpretations cross-validation can enable. Once you are generating fold scores correctly, the spread among those scores becomes one of the most useful signals you have, and it should not be dismissed as mere noise. High variance across folds often indicates that the model is sensitive to which examples it sees during training, which can mean the dataset is small, the decision boundary is fragile, or the features are not consistently informative. Low variance suggests the model behaves similarly across partitions, which usually reflects stability and better confidence that the mean score is representative. This is why it is dangerous to report only a single number, because a mean without context can hide a model that performs brilliantly on some folds and fails badly on others. In practical terms, fold variance is an early warning that your evaluation might be overconfident, and it can guide you to seek more data, improve feature engineering, or select a simpler model that generalizes more consistently. Choosing the value of k is a trade-off between how efficiently you use data and how much computation you can afford, and you should be able to justify that trade-off rather than defaulting to a habit. When k is larger, each training run uses a larger fraction of the data because the validation fold is smaller, and that can reduce bias in your estimate of generalization. The cost is that you train the model more times, and if the model is heavy, the total runtime can become impractical. When k is smaller, you reduce runtime, but you increase the dependence on larger validation chunks, which can raise the variance of the estimate and reduce how much training data each fold gets. A useful way to think about it is that k controls how many perspectives you take on the same dataset, and you need enough perspectives to avoid being fooled while staying within your compute budget. The temptation to make decisions based on the best fold is one of the most common ways teams accidentally turn cross-validation into a score inflation tool. If you train k models and you cherry-pick the fold with the highest validation score, you have not estimated generalization. You have selected an outcome that benefited from a favorable split. That is essentially the same mistake as running one split many times until you get a good number, then pretending it was the first and only attempt. The correct interpretation is that each fold score is one sample from the distribution of possible outcomes, and the mean is a summary of that distribution, not a target to be gamed. If you ever find yourself celebrating a single fold result, treat that as a signal to slow down and return to the purpose of the method. This is also why you should avoid selecting a model purely because it produced one unusually strong cross-validation run, especially when comparing multiple algorithms or feature sets. When you compare many candidates, the probability that at least one of them gets a lucky evaluation by chance alone increases, and that is a form of multiple comparisons that can mislead you. Cross-validation reduces luck relative to a single split, but it does not eliminate the risk of overfitting your selection process to your evaluation procedure. The discipline is to compare candidates using the same cross-validation scheme and to focus on consistent improvements in the mean along with reasonable stability across folds. If a candidate wins only because it had a spike in one fold while performing similarly or worse elsewhere, that is not a reliable advantage, and it often disappears on new data. A major strength of cross-validation is that it supports systematic hyperparameter tuning, because it gives you a robust way to evaluate each hyperparameter setting. Hyperparameters are choices you make about model structure or training behavior that are not learned directly from the data, such as regularization strength, tree depth, or learning rate. If you tune hyperparameters on a single validation split, you can easily select settings that fit that split's quirks rather than general patterns, and your tuned model may disappoint when it matters. Using K-fold cross-validation for tuning means each candidate setting is evaluated across multiple folds, so the selection is driven by repeatable behavior rather than a single favorable partition. This does not guarantee you will pick the globally best setting, but it greatly reduces the chance you pick a setting that only looks good due to split luck. Even with careful tuning, you still need a final test set that remains separate from the entire cross-validation and tuning process, because otherwise you do not have an independent confirmation. The role of the test set is to provide a one-time, unbiased estimate of performance after you have finished choosing the model family, the features, and the hyperparameters. If you repeatedly check test performance while tuning, you gradually leak information from the test set into your decisions, and the test set stops being a true holdout. The clean workflow is to use cross-validation on the training data to guide tuning and selection, then lock the choices, and only then evaluate on the untouched test set. That separation is a governance habit as much as it is a technical habit, because it preserves the credibility of your reported performance. When you communicate cross-validation results, reporting the mean alone is a classic way to accidentally mislead your audience, even if you have no intention to do so. The mean is helpful as a central tendency, but it does not express uncertainty or stability, and stakeholders often interpret a single number as a promise. Sharing the spread, whether as a standard deviation, a range, or a simple description of how much fold scores varied, gives a more honest picture of expected performance. This is especially important when comparing models whose mean scores are close, because a tiny difference in means may be meaningless if the fold-to-fold variation is large. Clear communication here builds trust, because it shows you understand the difference between an estimate and a guarantee, and it helps decision-makers weigh risk appropriately. It is worth anchoring the core memory for this topic in plain language, because the exam will often test the intent behind techniques, not just their mechanics. Cross-validation exists to reduce luck from one split, not to inflate scores, and any practice that turns it into a score-boosting trick is a misunderstanding of its purpose. If you preserve the boundaries, avoid leakage, respect time order when time matters, and interpret variance as information, cross-validation becomes a reliable estimator of generalization rather than a vanity metric generator. The method gives you repeated evidence about how a model behaves under different partitions, and that evidence is most valuable when you treat it as a window into uncertainty. In other words, cross-validation is a humility tool, and the most mature practitioners use it to avoid fooling themselves before they have the chance to fool anyone else. To close episode 81, titled Cross-Validation, K-fold Logic and Common Misinterpretations, it helps to be able to describe the steps of K-fold cross-validation aloud in a way that proves you understand what is happening. You divide the data set into K folds, train on K-1 folds while validating on the remaining fold, repeat until each fold has been the validation fold once, and then summarize the K results with an average and a measure of spread. When you can say that smoothly, you are much less likely to confuse cross-validation with a one-time validation split or to misuse the fold scores as if they were independent test results. A clean pitfall to remember is leakage through preprocessing that was fit on all data before folding, because that single mistake quietly turns evaluation into self-deception. If you keep the goal in mind, which is reducing luck rather than inflating scores, you will use cross-validation the way it was intended, and your results will stand up when it counts. Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.